Good afternoon, everyone. I'm Shuo. I'm going to present our work XO today, which is remote TCP connection offload and applications. So some context first. As many of you has already know that in data center or cloud environment, load balancing work usually happens at multiple levels. For example, closer to clients, we have layer 4 load balancer, which is operating at flow granularity. And closer to servers, we have layer 7 load balancers. They are operating at the request granularity. So our work, XO, we focus on layer 7 load balancers. Compared to layer 4 load balancer, layer 7 load balancer is much more expensive. This is because it acts as a proxy who terminates client connections first, and then it has to do some TLS decryption and also parse some like HTTP request, and then looking at what is the real payload in the packet, and then select a backend server based on whatever load or content itself. And its data path is complex. Like what it shows in the figure, packets always goes up and down in the network stacks, crossing the kernel and the user space boundaries multiple times. Our work XO, we enable lightweight packet level processing at the layer 7 load balancer for ingress traffic. And for egress traffic, we XO enables direct server return that completely bypass the layer 7 load balancer. As a result, XO can dramatically reduce the CPU and network bandwidth, which otherwise could be on the and also, XO can better utilize the backend server resources, which otherwise could be underutilized. And in the rest of this talk, we are gonna present how this architecture is achieved. So there are some existing work on improving performance of layer 7 load balancer-based systems. So for example, works including Prism and Capybara, both of them rely on programmable switch. And programmable switches, they are normally useful for operator tasks, for example, like monitoring or telemetry. However, it is unlikely that the host applications have access to programmable switches programmability. And there are also other works, but all of them, they kind of like lack of some functionalities. For example, they might lack of direct server return, or they don't have any TLS support, or they cannot be ported to real-world application. So now let's introduce how XO works. So first, the layer 7 load balancer accepts TLS TCP connections, and then it decrypts and reads the request sent by the client, just like what regular layer 7 load balancer do. And then the layer 7 load balancer selects a backend server that can handle this request based on content or load. It then serializes the TLS or TCP connection and then transfer it to the selected backend. Layer 7 load balancer then installs a packet redirection rule in its packet level, packet IO level, or NIC, so that the future packets in the connection from the clients will be redirected to the server. So finally, the server restores the TLS TCP connection and sends back the response directly to the client with the source IP address of the layer 7 load balancer. Then for X or the next request, the packet redirection rule installed earlier will redirect all of this to the selected server. Here's one thing to note is that upon the next request, the application might want to return the connection back to the layer 7 load balancer when that backend server is overloaded or just simply because it doesn't have the requested content. And in this case, the system state will just go back to the leftmost picture in this slide. So one design highlight of XO is how to redirect the ingress packets to the server. So we actually have two options. The first one is using eBPF. It is fast to install a rule because it's just doing this by updating shared memory, which is called map. However, packet redirection rate with eBPF is not that good because this happens all within software, and unfortunately it consumes some CPU cycles. Second, we have choice of using TC Floor, and we can use TC Floor with sneak offloaded feature. But this takes time to install a rule because it involves hardware reconfiguration. Therefore, we propose a software-hardware hybrid approach. So we install the packet redirection rule in both eBPF and TC hardware. As shown in the left, eBPF starts operating immediately, and eventually, once the hardware rule with TC Floor becomes active, then all the packets will just go through or be redirected by the NIC without going up to the eBPF. Another design highlight of XO is a cancelable queue. As we mentioned earlier, servers at some point may need to return the connection back to the layer 7 load balancer. And this needs the withdrawal of both hardware and software rule. Otherwise, packets might be continue to redirect it to a server, even though that server is no longer owning the connection. But the problem here is that hardware rule withdrawal may take some time. Because the TC Floor commands are globally serialized in the kernel and cannot be offsite in the queue. This is especially serious in a case where connection needed to be returned to the layer 7 load balancer after a server only capable of serving a very small amount of requests. So it's possible that the connection has been migrated back, but the hardware rule insertion command is still in the queue. So as a solution, we move this command queue to the user space. And because command queue now sits in the user space, we can easily cancel any no needed command. And this is just a multiple producer and single consumer queue. XO worker threads push their rule commands into it, and a single dedicated thread just pop those commands out and send to the NIC one by one. So now let's look at some application porting experience. We found that currently existing connection migration-based systems like Prism and Capybara we mentioned earlier, they never ported existing real-world application. And because the application modification is fundamental limitation with such connection migration approaches. So we think it is important to see how hard it actually is. So we ported nginx and Ceph because they have different features. Nginx is like reverse proxy with replicated backend, and the Ceph is distributed object storage systems with partitioned backend servers. We show more details in the paper, but one thing we'd like to mention is that the use of kernel network stack make this application porting much more easier. This is mainly because we can, with this standard kernel, Linux kernel APIs, we can preserve file descriptor semantics, and we can preserve the whole application threading model entirely. This is said if we opt for kernel bypass techniques or stacks, then the application porting would become much more harder. So now we report the performance. Overall, XO's performance depends on state transfer frequency determined by object size or the number of requests processed by the same backend continually. We use a conventional proxy as the baseline. XO eBPF here in the figure is the XO with eBPF support only. Support, I mean, we only use eBPF itself for packet redirection. XO CX5 here is with the hybrid packet redirection with NVIDIA Connect X5 NIC. And XO AGI here in the figure uses the Metronome Agilio NIC. When state transfer occurs for every request, as shown in this plot, we see that XO eBPF outperforming proxy from 128 kilobytes objects. It's saying XO eBPF overtakes the hardware variants at small object sizes because its raw installation is pure software. So it means that there's no need to wait for NIC hardware reconfiguration. So with 2048 kilobytes or larger objects, XO Agilio outperforms XO eBPF because of its hardware-based redirection. XO Agilio always achieves better performance than the XO CX5. This is because its hardware reconfiguration is faster, as we measured earlier. Taking a look at the red graph where state transfer is less frequent, or here is we do the state transfer every 20 requests. We can see the hybrid methods outperforms proxy with smaller objects. We also start to see the hardware-based packet redirection benefit with smaller objects. This is the CPU usage of the layer 7 load balancer and one of the servers when the state transfer occurs for every request. So with small objects, state transfer overhead is high, so layer 7 load balancer shows higher CPU usage with XO. But otherwise, the XO reduces layer 7 load balancer CPU usage while achieving higher throughput. So hardware packet redirection further reduces the layer 7 load balancer CPU usage. Here is state transfer latency breakdown. In total, it takes 225 microseconds, excluding hardware reconfiguration. Here we opt for unmodified Linux TCP IP stack just for easy deployment. But if we modify that, we can actually cut the latency of connection, serialization, and restoration. This is because the current Linux API takes multiple system calls for these two operations. So each of them require a separate socket log, which takes a lot of time. To verify this, we implemented consolidated TCP state serialization and restoration syscalls, which performs all the operations on the one single log and system call. We confirm this calls, this one single system call improved the XO performance significantly. As shown in the graph, it shows that the effect of those calls on XO eBPF, and it demonstrates higher throughput, showing the lines, and also lower latency, showing in the bars. Now we show the nginx throughput and layer 7 load balancer and server CPU usage. Thanks to the network bandwidth utilization and reduced layer 7 load balancer CPU usage, we confirm that XO improves their throughput. We see higher CPU usage at the servers than vanilla nginx. This is simply because they are sending data at higher throughput. Here is Ceph throughput and CPU utilization. It also achieves better performance with XO. Now we discuss some design and deployment implications of XO. So first is how to use XO in virtualized environment or virtualized network infrastructure, which is the case in many clouds. So when you have a bare metal instances, we can likely use the TC floor offload in the NIC. But if our hosts are virtual machines, then it is unlikely, unless NIC hardware is exposed, for example, with SR-LV. However, we demonstrated that XO still achieves good performance, even just with eBPF. So in our current implementation, we are not migrating congestion control parameters like window size and measured RTTs, simply because the Linux kernel doesn't expose those parameters for serializing TCP state. So as a result, migrated connections perform slow start. This also means that we reported conservative estimate of XO performance. So in future work, we'll add these parameters into the migration. So in a summary, in summary, we presented XO a new approach to accelerate layer 7 load balancer-based systems with better backend server resource utilization and streamlined data paths. You can find more details in the paper, and our code is online. We are also gonna presenting our follow-up work in tomorrow's poster session. So welcome to the poster session if you'd like a talk or just a simple chat. And that's it. Thanks for listening. I'm open for any questions. Happy to take any questions if you have.